concepts. And the first of these concepts is how do we define and demarcate directions inside crystals. So there are set procedures for demarcating directions inside crystals. Directions, as you know, are vectors. So if you have some crystal structure, suppose I draw a cubic unit cell in which this is my origin and I have demarcated my lattice vectors A, B, and C along these directions. So this is how I've defined the origin and the A, B, C. So the directions are very simple to specify. The direction, of course, is represented by a vector. So if I talk about this direction along the A, this is denoted as 1, 0, 0, and it's put inside square brackets. Okay. So this really means that you move one unit along the A axis and you don't move at all along the B or the C axis. This would be obviously the 0, 1, 0 axis. This would be the 0, 0, 1 axis. The space diagonal would be the 1, 1, 0 axis. Direction. The body diagonal would be 1, 1, 1, and so on. So this is how all the directions are specified inside a crystal. And you can talk about negative directions as well. So this direction that is diametrically opposite to 1, 1, 1 is represented as 1, 1, 1 with a bar on all three of these. Okay? This direction here would be 0, 1, bar 0. Minus. Right? If I were to look at a direction that originates at the origin and say intersects this edge at 1/2, then this direction would be represented by so the intercept with the A axis is at 1, the intercept with the B axis is at 1/2, and the intercept with the C axis is at 1/2. So then you rationalize these indices and you write 2, 1, 1 as this particular direction. Okay, so all the indices are rationalized. So this is how directions are specified inside any crystal system. And this does not only apply to the cubic system, you can have directions specified along any unit cell belonging to any crystal system. For example, if I consider the monoclinic unit cell, this is my origin over here, then the direction, say 3, 2, 1 would be so you move 3 units along along the A axis, 2 units along the B axis, and 1 unit along the C axis. So can you draw this particular direction in this unit cell?
दो एक्सेस के थोड़ा सा चेंज नहीं आएगा फिर मतलब एक आई थिंक बी सेम रहेगा लेकिन ए एंड सी फर्क हो जाएगा या वर्क सेल के हिसाब से ए बी सी को सेम रखना है.
So what you need to do, what I can do is break this up into 3 parts. break the b-axis into two parts, right? And this into just one part. So when this has moved 3 units along the a-axis, you have moved 2 units along the b-axis and 1 unit along the a-axis. So this is this particular direction, 3 to 1. Connect the origin to this point. Then you move 3 units along x-axis, where you move 2 units along. So this, all of this is in fractionalized, normalized with respect to the length of the unit cell. So if I were to consider this in 2D, this is my a-axis and b-axis, let's say. And this is 1 unit cell along A, 2 unit cell along A, and 3 unit cells along B. So this is a unit cell. Okay? This is the size of my unit cell. So this is 1, 2, 3. So my direction is specified by square bracket 3, 2. So I move 3 units along here and 2 units along here. Okay? This is my direction. 3 steps along A and 2 unit translations along B. This is how directions are specified. Okay? But in this particular case, since I have a 3D example, I also move 1 unit along B. So I move 1 unit translation C along B.
सर मोनोक्लिनिक यूनिट सेल है ना, तो ए और बी एक्सिस ऑर्थोगोनल तो नहीं होंगे ना?
नहीं, ये कोई एंगल है नॉन 90 डिग्री। ठीक है, अलबत्ता ये एंगल 90 डिग्री है और ये एंगल भी 90 डिग्री है। Alright, so this is how direction is specified. By the way, if I were to specify this direction 2, 1, 1, there will be an infinite number of lines that can be drawn parallel to this. So the direction is just a direction. So I can draw an infinite variety of lines parallel to this in any plane whatsoever. All lines that are drawn parallel to this will be designated by the same indices, 2, 1, 1. Okay? Now, if you look at the cubic crystal system, all edges are the same. Let's talk about the edges. So, if we look at the edges that bound this unit cell, so there is, of course, 1, 0, 0. There is 0, 1, 0. There is 0, 0, 1, correct? And then there are the directions that are just the opposites to these. So all 6 of these directions, in this particular case, that happen to lie along the edges of this cubic crystal lattice. This cubic system, these are the edges. So it is specified the direction along this edge, along this edge, along this edge, and in the opposite senses as well. So all 6 of these directions, as far as the cubic is concerned, they're equivalent. There's really no difference between them because A, B, and C are just the same, and all 3 of these angles are also 90 degrees. So there is really no difference. If this structure were truly cubic, then all 6 of these directions will be equivalent. They will belong to a family of directions. Correct? Because there's no way to tell whether you're moving to the left or to the right, up or down, along an edge. So all 6 of these directions belong to a family of directions, which can be, that family of directions can be represented simply by any any of these symbols, 1, 0, 0. And since it's a family, you can put this inside these angle brackets. So this is a family of directions. In the tetrahedral system, since A, B are equal and they're unequal to C, so this family, this will be one family. And these two directions will belong to a different family because C is not equal to A and C is not equal to B. So the C direction is distinct in the tetrahedral case. Okay? In the hexagonal, exactly the same thing applies, and so on. So you can have directions, you can have family of directions. And I'll give you some homework problems to experience these directions.
सर तो यूजली जब भी हम कोई मोटिव या डिफाइन करते हैं गाइडेंस लैटिस के लिए तो हम बस एक फीचर से फिर फैमिली ऑफ डायरेक्शंस को वो
ये मोटिव तो लैटिस पॉइंट्स पे आता है। इस वक्त हम सिर्फ क्रिस्टल के अंदर जो डायरेक्शंस हैं उनको स्पेसिफाई कर रहे हैं। Because properties depend upon directions, and this dependence of a property on a direction is called anisotropy. Therefore, it's really important to specify what direction that we're talking about. Crystals have different properties, solids have different properties in different directions, in general. Alright, so we know about the body diagonal direction, this is the body diagonal direction. What about a face edge or a face diagonal? A face diagonal in the cubic system will have a direction of this kind, 1, 1, 0. And so on. Yes, please.
So the 0, 0, 1 of these two crystals won't form a group.
Sorry?
The 0, 0, 1 direction of these two crystals, left and right. Because of the crystals, the right one. The 0, 0, 1 of these two won't form a same group.
Won't form
Form the same group. They will be different.
directions have nothing to do with the group.
I mean, there's a group that you can.
These ones?
Yes.
No, they will. So this direction, in this monoclinic system, this direction and this direction are the same. They belong to the same family. There's really no difference whether you go up or down, because it's a lattice.
And if you compare this with the 0, 0, 1 of the cubic,
Of this, of cubic, then these also form a family, but for cubic, all 6 form a family.
सर I think वो पूछा कि if they're the same things, we consider them similar.
What do you mean it's similar? This is a direction, a crystal you're talking about. What do you mean by similar? So you have a crystal, and you're talking about which direction you want to specify in a crystal. Okay? In a cubic system, there will be a family of directions associated with the body diagonal. So that family will be denoted as 1, 1, 1. It goes within these brackets, and this will comprise the directions 1, 1, 1, 1, 1, 1 bar, 1, 1 bar 1. Right, and likewise we can have 1 bar 1, 1, 1 bar 1 bar 1, 1 bar 1 bar. You can also have all 3 of them. One,
Copy 1 bar 1.
right. So all 8 of these form a family of equivalent directions in the cubic system. So this means that if I draw a cubic unit cell, four kinds of body diagonals can be drawn, correct? So here is one. This is one direction. This is another direction. A third direction. Sorry. And fourth. These are four directions corresponding to the four body diagonals. So you take these four directions and then you take the opposites to these. So you get 8 directions in total. All 8 of these directions are just the same. If there are atoms inside this crystal structure, then walking along any one of these directions, you get the same distribution of atoms, with the same spacing. Try. So this के लिए ये सिर्फ क्यूबिक की बात होती है, ठीक है? तो diagonal के लिए there will be some body diagonals will be so along this connecting A B with C will be the same. There are two ways to connect it. So this will bifurcate into smaller families. So this is how direction is specified. Any questions about directions? Because all of this is going to be useful as we continue our discussion on crystal calculus cases.
So what if we take a direction which is parallel to one of the diagonals but not exactly on the diagonal? Would we have to
It's the same direction. Direction is just a direction. You can take a vector and place it anywhere by keeping it parallel to the edge.
you would have same distribution to all these?
No, that's not true. So only when you have a direction and then you move along a unit translation, you will get the same distribution of atoms. However, if you have directions belonging to the same family, then you will have the same distribution along all directions in that family. Okay, so now let's talk about planes. So far so good. So we've talked about directions and now planes. Now these indices for directions, these are also called Miller indices. For planes we also have designators. They are also called Miller indices. So planes and directions are described by very similar notation. Directions are enclosed within square brackets and families of directions within these angular brackets. Planes are enclosed within parentheses and families of planes within curly brackets. So let's look at planes. So in order to describe planes, I will first kind of show examples in 2D or projections of 3D crystals in 2D. The simplest of them all to describe is the cubic plane lattice. So I look at the projection of the cubic on to the blackboard plane onto the C axis. So this is my A, this is my B. Now a plane is a plane. So suppose I draw a plane like this. So there will be planes parallel to this. So there will be sequence of planes. Now I want to designate what these planes are. So this is one family of planes. I could draw another sequence of planes. It's another sequence of planes. Alright? And these planes can have different spaces. So let's first of all look at these planes. So if I move from A along A and I traverse one complete unit translation, I start from the origin, I traverse one complete unit translation, I see along A, I see one crossing. I see one crossing. That is, this plane crosses me. As I move from here to here, I see it crossing once. So I write 1. As I move along the B axis, I never see a plane that crosses because I'm moving actually parallel to the plane, so I put 0. And if I move along the Z axis, the C axis, since the plane is kind of out of the plane of grid, I still do not see it crossing. So I write another 0. So these planes will be designated as 1, 0, 0.
So the rule is कि अगर वो perpendicular हो तो 1 करते हैं, अगर parallel हो तो 0 करते हैं.
अभी ये बात समझ आ गई, अभी थोड़ा सा आगे ठीक है. So these are planes that are along the C direction. So I move along A, I count the number of crossings. I move along B, I count the number of crossings. I move along C, I count the number of crossings. In this example, when I move from the origin to here, I encounter 2 crossings. So I put 2. When I move from along B, I also encounter 2 crossings. 2, 2, correct? And along C, I don't encounter any crossing. So these planes, this plane, all of these planes have the Miller indices 2 to 0. Alright? This one? So I have the origin, I stand at the origin and I move along the A axis. So this is my unit cell A. This is lattice point here and a lattice point here. So when I start my journey along A, I encounter the plane once and then twice. So I put 2 here. Likewise, when I move along B, I encounter 2 planes. I encounter 2 crossings. 2, 2, and none along C. So the mirror indices for these planes is 2 to 0.
So इसको 1 1 0 लिख सकते हैं या
Right. So this is the same as 1 1 0. I'll talk more about this later, but this is the same as 1 1 0. The only difference is that if I were to draw 1 1 0, so these are the planes 1 1 0. So there's a plane here and a plane here. So this sequence of planes in yellow is 1 1 0. So 1 1 0 and 2 2 0 are parallel to one another. The only difference is that the perpendicular distance between 2 planes here is, let's call it D 1 1 0. And the perpendicular distance between these planes, D 2 2 0, is different. So this distance is twice of this distance. But these planes are parallel to one another. Okay? So they are parallel to one another, but the distance between these planes, the normal distance between 2 successive planes is different. Okay? Another way to generally in textbooks how they define Miller indices is that you look at the planes and see where the first plane intersects the A axis. It's at 1/2 of the A dimension. So 1/2 here, 1/2 here, and it doesn't intersect on the C axis. So you have these numbers 1/2, 1/2 infinity, and then you take the reciprocal, like 2 to 0. So that's also another method of designating the Miller indices. Let's look at some more examples. So I want to draw these planes 3 to 0. There you go. These are the 3 to 0 planes, right? So I've subdivided this into 3 parts, and this is how the planes cross. I've subdivided this axis into 2 parts. Okay. These are the 3 to 0 planes. So what about 3 bar to 0.
Let diagonal section.
So these planes will be of this kind. Right? So 3 bar to 0 is the same as, by the way, write this as 3 bar to 0 or 3 2 bar 0. It's the same thing. Now, where does this negative sign come from? An easy way to remember this, there are two ways. First of all, you see where this plane what you could do is, suppose this is my origin, I start from the origin, I am going to move along the a-axis. So I cut the plane, it's like a needle that is piercing a piece of cloth. I cut that plane from the top, right? And when I move along the B direction, I cut the same plane from the bottom. So once I am piercing the plane from the top, and when I move along B, I am piercing the plane from the other side. Here, if I move down or from left to right, I am cutting the same plane from the same side of this fiber, of this cloth. Right? So that's why these two directions, these two numerals, both with positive sign. Here one of the signs is inverted. And these planes are of course different from these planes. Alright? Now I can, yes please. कौन सी बात ये वाली? Negative. देखो I have two origin. I'm starting here and I traverse downwards. So this piece of cloth has two sides, one above and one below. So I'm hitting this surface from above. But when I move along the B-axis, I'm hitting the surface first from the bottom. So I'm hitting the surface from two opposite sides when I move along here along B. Therefore, these indices must both be, they cannot be have the same sign. They must have different signs.
उसी हिसाब से वो इक्विवेलेंट है कि -3 -2.
Might right. बिल्कुल. Okay. So another way to look at this, if you look at this plane here, it intersects the a-axis at the negative intercept and the b-axis at the positive intercept. So if I extend this backward, it intercepts this axis at the negative number, if this were my origin, and this b-axis at a positive number. A at a positive, and this b at a positive, and a at a negative. Okay, that's another way to look at it if you are used to thinking in terms of points of intercepts. Now let's look at a few examples in 3D. Once again, let me draw the cubic unit cell. Suppose I want to draw the 1, 1, 0 plane. What would that plane look like?
The bottom is
This plane, right? That's the 1, 1, 0 plane.
the bottom.
It intercepts a-axis at unit length, b at unit length, and doesn't intercept z. So it's parallel to z. 1, 1 bar 0 will be this This top plane, this plane. What will this plane be at the top? And likewise, all planes that are at the top C faces. 001. This plane could be designated as 001 bar as well, or 001, it doesn't matter, since it's just one non-zero number here. What about 111? That will be this plane over here. Right, this plane, slanting plane. Can you attempt to draw say, let me draw an orthonormal cell. What about the 400 planes? Very good. So this will be the black plane here, and then you draw 4 planes. So these 4 planes that are disposed at 1/4 of the edge length along the A-axis, they will be the family of 400 planes. To make and you try to draw the 322 plane. So this family of planes in this orientation will be the 322 planes, because this distance is 1/3 of A, this distance is 1/2 of along B, and 1/2 along Z. 322. As you move from origin here to here, you get 3 crossings. There will be another one over here. Right? These are how these planes are disposed inside this unit cell. Okay? If I were to make this 2-bar, probably I'll make that in the fourth. Okay, so this is how these Miller planes, these indices are defined. And then you have families of planes. For example, in the cubic system, all 6 faces are equivalent. Right? So all 6 of those can be designated as 100. Pixels. So this family of planes 100 will be 100, all 6 edges of the unit cell. So they will form a family of planes. So this is how directions are specified and how planes are specified. Now, if I talk about directions and planes together, in the cubic system, things are really easy. Only in the cubic system, if I have a plane HKL, Miller index is HKL, it's only valid for cubic. Then the direction HKL is going to be perpendicular to that plane. This is only true for cubic. For example, if in the cubic system I have the plane suppose I have the plane 1, 1, 1. This is the plane in the cubic system. This is the slanting surface. Then the direction 1, 1, 1, which is along the body diagonal, is going to pierce this. In fact, like this, in such a way that it's perpendicular to the plane. But this is only true for cubic system. It's partially true for tetragonal, partially true for orthogonal. For example, if I look at the tetragonal system, so in the tetragonal system, in the tetragonal system, the A and B are equal. So suppose I draw a projection, a phenographic projection of A and B. So these sides are equal, right? This is equal to this. Suppose I draw this plane. This is a plane. This plane is 1, 1, 0. And what about the direction 1, 1, 0? That's simply this direction here, 1, 1, 0. Right? And both of them are perpendicular. The direction is perpendicular to the plane. But if I take the other side for the tetragonal system, suppose this is my B and this is my C. Then if I want to draw this plane, right? What is this plane? It's parallel to A. So it's 0, 1, 1. This is 0, 1, 1 plane. Remember, I've drawn the projection as seen from the A axis. So this is B, this is C. And this is the tetragonal system, and B is not equal to C. ठीक है ना? Tetragonal को आप दूसरी ज़ाविये से देखो. So this is the 0, 1, 1 Miller plane. Now if I were to draw the 0, 1, 1, 1 direction. So 1 unit on B, 1 unit on C, this will be this particular direction. And this is not going to be 90 degrees. Because it's a tetragonal system. So only for the cubic system we have the case that the directions which have the same indices as the Miller indices for the plane, they are usually perpendicular. So the direction is perpendicular to the plane. Yes, please. There will be specific angle, yes. Some angle, which can be computed from geometry.
It will be the same for all the planes and lines for the tetragonal system.
So if I replace this B with A, you get a similar configuration. Alright, so now we've discussed directions, we've discussed planes, and now there are certain rules you would like to know. And these stem from simple geometry. The first rule is, just want to state out these rules, that a direction UVB, some direction UVB, will belong to the HKL plane if the dot product between these vectors is 0. If UH plus VK plus WL is 0. Right? So these are ideas that come out from simple geometry, and this is valid for any crystal system, for all the 7 crystal systems. The second is that, and you can look at many examples of this. I'll give you some homework problems as well. Two planes, whenever you have two planes in the system, those two planes will always intersect. Any two non-parallel planes will intersect, and they will intersect along the line. Okay? So if you have two planes, H1, K1, L1, and H2, K2, L2, then you form this matrix and you want to find the point of the line at which they intersect. You form this matrix, okay? And then the direction will be given by U will equal K1 L2 minus K2 L1. V will equal minus of H1 L2 minus H2 L1. W will equal H1 K2 minus H2 K1. Right? If you have two directions, they will always lie in some plane. If you take two arbitrary non-parallel directions, they will lie in some plane. You can find that plane as well, the indices of that plane. So if you have two directions, U1, V1, W1, U2, V2, W2, then they will lie in some plane whose mirror indices will be HKL. We form this matrix. H will be equal to V1, W2 minus V2, W1. K will be equal to minus of V1, W2 minus U2, W1. L will be equal to V1, and so on. You can have multiple planes, more than two planes. You can have 3 planes that also intersect. Let me give you one example of that. So these are geometrical considerations. You just need to note down and apply them. These come out from simple geometry. You can find whether 3 directions are coplanar or not. That can be tested by putting all 3 directions U1, V1, W1, U2, V2, W2, U3, V3, W3, and finding this determinant. If this equals 0, then these 3 directions will be coplanar. Okay? So a lot of geometric calculations could be actually be done. So one example I would just like to highlight is about the zone. Suppose I am considering the cubic system and I have 3 planes. Let me draw those planes. So I draw this is so let me draw one plane like this. This is one plane, okay? Which plane is this? 1, 1, 1. Then I draw this plane. What plane is this? 1, 1, 0. Right? You can see they're intersecting here, right? Let me draw yet another plane. So two planes are now intersecting, and then what you could do is you could find out this direction. This direction will be given by this rule number 2. You can find UV and W. This direction will be, as you can immediately tell, what will this direction be? What is this direction? One bar 0. Right? So this direction is 1 bar 0. So they intersect at 1 bar 0. You can yet draw a third plane, which is this particular plane. So what is this? So this particular plane is 1, 1, 1, and the yellow plane is 1, 1, 1 bar. Okay? So you have to make that distinction. Okay? So when you take these three planes and put them together, they are intersecting at this point, at this line. So these planes belong to, they said they belong to a zone because all three of these planes are intersecting on a zone axis. So the planes look like this. So there's one plane here, another plane here, and the third plane here. And all three of them are intersecting at the zone axis. That zone axis is this direction, 1, 1, 1, 0. Okay? So, three planes can intersect. Now I would like to move on to the next topic of, so once we have this familiarity with how to specify directions and specify planes inside a crystal structure, we would now like to do something useful with all of this. And in order to see kind of, which will be the next part of this lecture will be slightly more mathematical. What we're going to do now is we're going to come up with this idea of, okay, you know how crystal structures are described. We know that there is symmetry, there are symmetry elements of different kinds in 2D and 3D. Those symmetry elements combine together, congregate together in 230 kinds of combinations that are called space groups. All the materials belong to those space groups. And there is a systematic way of reading the space group descriptions in the international tables. And then we can also specify what direction we're talking about inside crystal structures and what planes are we talking about. Now this is how we describe crystal structure. This is all that there is that is required to describe the arrangement of matter inside solids, crystalline solids. Now once you do homeworks, everything will be clear, you get the hang of it. And you can visualize, you can start visualizing with the help of some computer aids of how these different structures are made. Now the question is, how do we know that a particular material has a structure? So can you guess how this is done? How do we know that zinc oxide belongs to a particular space group? Zinc sulfide belongs to a particular space group. Zinc belongs to a particular space group. Zinc triselenide belongs to us. How do we know that? Experimentally, of course, but what kind of experiments do we need to do? Microscope, but microscopes can't show you where the atoms lie. And seeking? In a little bit.
Magnetism is
देखो ठीक कह रही है you shine some kind of radiation onto the solid and then see how that radiation is scattered.
XRD.
Right. So one way is to shine X-rays and see how the X-rays diffract from the crystal. So diffraction takes place, which means you have, when you do diffraction with light, how do you do diffraction with light? You kind of have, say, a grating. Talking about transmitting grating, you have slits inside an opaque solid, and then you put light onto this. And I'm exaggerating all the dimensions here. These slits are really, really small, comparable to the wavelength of light. And if then you put a screen somewhere, you have a screen here, and you look at the pattern of intensity that comes out from this incident light, what do you get? You get fringes, you get bright spots and dark spots. Roughly. And there is a particular spacing between these spots and a particular spacing between the slits. Suppose this is A. Generally what you will find that this spacing between the patterns will be proportional to 1 over A. So if these slits get tighter, this becomes wider. So this phenomenon is generally called diffraction. And what happens is that light is coming in, it is a wave. And then when it passes out from this wave, certain regions are blocked. When it comes out from these slits, whatever wave exists here interferes with itself. And that interference causes regions where the interference is constructive and where it is destructive. So because of the wave nature of this impingent radiation and the periodicity of this structure, you get a nice pattern. That's the periodicity. Now crystals, of course, are the epitome of periodicity. Everything is arranged in a very nice symmetric fashion. So they act like gratings. They act like gratings for radiation. X-rays, if you shine X-rays, X-rays are of course electromagnetic. Short wavelength, and they are electromagnetic. And what they would do is that they would interact with the electron cloud. Okay? So electrostatic interaction, and iron, nickel, all of these elements have their own electronic structure. And they are arranged in a periodic fashion dictated by the space group to what that material belongs to. So when that light X-ray will scatter off from that material, there will be certain directions in which light is going to come out and will be blocked in others. Exactly the same fashion, light is coming out only along certain directions. So along this direction, along this direction, along this direction, along this direction. So space has become quantized in the sense that only certain directions are being allowed, which light can scatter. So you shine some kind of radiation onto solids, and you can tell by looking at the directionality of scattered radiation what the structure of that solid is, what space group does it belong to. And then it becomes an inverse computation problem. You get a scattered pattern, and from that you have to infer the structure, the space group. So the space group is all that there is. The space group and the position of the atoms, or the Bravais lattice and the motif. These are two equivalent descriptions. That's all that you need to completely describe the structure. Now it's possible, so if I will show you some real X-ray diffraction patterns as well. But if, just to motivate the idea, you have certain angles at which diffraction takes place, so you get these peaks. Right? So this is the intensity of scattered X-ray along certain angles. This is called an X-ray diffraction spectrum. So you get peaks scattering at certain angles, theta, certain angles. And these intensities are also different. So by looking at the position of the peaks, you can tell which Bragg lattice the structure belongs to. And by looking at the height of the peaks at those positions, you can tell what kind of elements exist. So this is called crystal structure determination through X-rays. And this pattern is called an X-ray diffraction pattern, XRD. So we have an X-ray machine in our laboratory as well. We'll probably take you to that diffraction machine as well, so that you can see these things in action as well. But then you can shine other kinds of radiation as well. You can shine neutrons. Neutrons interact with the nuclei. Because neutrons are spin-full particles, they're spin-half particles. They interact with the nuclei, which can also have spin or protons. So they are also diffracted. So neutrons are produced in a particle accelerator. X-rays are produced in a cathode ray tube. But you can do neutron diffraction as well to find out the structure. You can also use synchrotron X-rays, which is this large particle accelerator in which electrons are accelerated and hard X-rays or very energetic X-rays are produced, which have extremely short wavelength. So all of this is done by diffraction studies. And of course you can look at the structure in the most remarkable fashion to electrons as well. Electrons are also waves. So you shine electrons on a crystal and you'll see that only electrons that are scattered in certain directions. This is what happens in a transmission electron microscope. So these are techniques that millions of physicists use, millions of chemists and biologists use to find out the structure of solids. Numerous Nobel Prizes have been awarded to this crystal structure determination problem, including the Nobel Prize to Watson, and they could discover the structure of DNA through X-ray diffraction. So we need to know about this. Okay. So now what we're going to do, what kind of mathematical tool do we have to describe the structure? So the pattern that comes out is in fact the Fourier transform of the structure. I'm going to explain this. So in order to describe this, I would like to use the concept of the reciprocal lattice. Any questions up to this point? Make things simple. Let me consider the monoclinic lattice, and I'm looking at the C plane, which means the plane which has the A and B axis. So okay. So these grid lines are just a guide to the array, not something real, right? This is the monoclinic lattice. This is the A direction. This is the B direction. All right. And these lengths may not necessarily be the same. Now we can draw planes inside. Suppose first of all I draw the C axis is coming out. First of all I draw the 1, 0, 0 plane. So the 1, 0, 0 plane is this plane, right? It can be this plane as well. They're all the same, belong to the same family, they're all parallel. So these are the 1, 0, 0 planes. Okay, now I'm going to construct this is what is called a direct lattice. This is a structure, the matter is juxtaposed on the direct lattice. The matter is the direct lattice. Now move on to another space. And that space is, suppose I take an origin, some origin in this case. I want to draw another lattice, so I need to have an origin. This lattice does not have any origin per se. Any point can be taken as the origin. Because all the points are equivalent. There is no difference between any of these points. You cannot say that, oh, I am just fixated to this point. That's not true, because none of the points is unique in a direct lattice. Okay? Is it possible? But that's not true for the reciprocal lattice. So I take some point, let's designate it as 0, 0, 0. In the reciprocal lattice space, this has the coordinate 0, 0, 0. Now what I would like to do is that I have these planes. I draw a vector, a direction that is normal to these planes. Right? That vector, of course, is going to point in this direction. This is 90 degrees. So starting from the origin, I draw a point along this vector. Okay? And I'll designate this point later. Okay, that's one thing that I done. Since my reciprocal lattice will also be three-dimensional and only have a 2D projection, I need another vector that describes the edge of the unit cell. So there's going to be unit cell in the reciprocal lattice as well. Self-repeating unit. If something is periodic, its Fourier transform, its reciprocal will also be periodic. So now what I do, I draw these things. What are the Miller indices of these planes? 0, 0, 1, 0. With indices put in parentheses, everything is rigorous. So now a vector perpendicular to these planes is kind of constructed, and I draw this vector over here, move a certain length, and draw another point. Okay. So now this point that I've drawn over here comes from the 100 family of planes. Okay, so I call this point as an index 1, 0, 0 in the reciprocal space. So this point is actually a proxy for all a family of planes. This family of planes has given rise to a point in the reciprocal space. This family of planes has given rise to this point, which I designate by the Miller indices of the corresponding planes. So this is 0, 1, 0. So I have described the direction in the reciprocal unit cell. Now the point is, how big is this cell? Because I know that this distance is A and this distance is B. Okay? Now the spacing between the 100 planes is A. So what happens is, in the reciprocal space, these points are separated by 2 pi over A. Some authors will write 1 over A, some will write 2 pi over A. Chemists and physicists have different conventions. Okay, doesn't matter.
Physics और convention.
जो मर्जी करो, मैं फिजिक्स को सुपीरियर नहीं समझता, जो मर्जी करो. So this is 2 pi over A, this is 2 pi over B, right? So whatever the plane spacing corresponding to those planes, the reciprocal of that demarcates spacing in the reciprocal space. Janaab. एक हाँ, तो इसके यूनिट्स हैं नैनोमीटर इनवर्स, मीटर इनवर्स, जो कि मोमेंटम के भी होते हैं, ठीक है, अगर h1 ले लें, so this is inverse of distance, ये नंबर है इसका, k है इसके यूनिट्स, ठीक है, so likewise if I draw another set of planes, so these are the 1, 0, 0 planes, if I draw planes which are in between, these will be the 2, 0, 0 planes. They have less spacing of a by 2. They will be further out on in this direction in the reciprocal space. So you get another point here, 2, 0, 0. So this reciprocal point corresponds to the 2, 0, 0 planes. Likewise, this reciprocal space can be constructed in 2D, right? You have defined the orientation of the reciprocal basis vectors, reciprocal lattice basis vectors. Let's call this vector A star, corresponding to the direction that is normal to the planes that are along that are do not intersect with A. And let's call this unit vector B star. Okay? So this entire reciprocal space can be built. And let me draw this reciprocal space. पीछे भी जा सकते हैं, जा सकते हैं. And the indices of these points. Now each point is distinct, unlike the direct lattice point. Each point is different from the other because it corresponds to a different plane spacing. So this point is 0, 1, 0. This point would be 0, 2, 0, 0, 3, 0. This point would be 1, 1, 0, 1, 2, 0, 1, 3, 0. This point would be 2, 1, 0. This point here will be 1 bar 0, 0. 2 bar 0, 0. This point will be 1 bar 1, 0. 1 bar 2, 0. This point here will be 1 bar 0. 1 bar 2 bar 2 bar 1 bar 0 and so on. So all of these points in the reciprocal space will have a particular index. This point itself in full glory represents all the 0, 3, 0 planes in here. This corresponds to this point here, corresponds to all of these planes. So I divide this into three distinct planes here. 1, 2, 3. 1, 2, 3. So I divide each unit cell along A into 3, bifurcate this into 3 parts. And these planes will have a certain distance which is B030, and this point here will be 2 pi over B030 units away from, right? Oh sorry, actually it's this point. ये वाला point, इस point की बात होगी 300. ठीक है यहाँ पे, ठीक है? So this is how the reciprocal space is built. And then you kind of move this into 3D as well. So you get 3 vectors, A star, B star and C star. And you generate the reciprocal lattice.
So ये discrete points हैं.
जी. Little discrete points and all इसमें और इसमें बुनियादी फर्क ये है कि लैटिस में सारे पॉइंट्स एक जैसे हैं, आप किसी को कोई आप लेबल नहीं दे सकते, कोई डेजिग्नेट नहीं कर सकते, because all of these points are equivalent, they're just the same. However, in the reciprocal space, all of these points are different. This structure is in the direct space, this is the same structure in the reciprocal space. Now you will have atoms on certain planes. We have atoms on certain planes, so that will reflect as a diffraction pattern in certain direction. Later on, we'll see that since this is related to momentum, momentum is related to direction, this is related to the direction of the scattered waves. This is the usefulness of the concept of the reciprocal space. In fact, a lot of condensed matter physics, dispersion relationships, has the starting point is the reciprocal space. So this is the basic idea of the reciprocal space. Just as A, B, and C define the lattice in the direct space, the vectors A, B, C itself define. In the reciprocal space, I have the vectors A star, B star, C star. And they can also be found out mathematically. A star is 2 pi over the volume of the unit cell in the direct space. Volume in the direct space. The volume in the reciprocal space will be the reciprocal of the volume in the direct space. A star is B cross C, right? So this is my A star. My B star is 2 pi over the volume in the direct space C cross A. This is 2 pi B A cross B, and keep in mind that my B is the volume in the direct space. Okay? So the volume in the direct space is say nanometer cube, the volume in the reciprocal space is 1 over nanometer cube. If you're talking about the cubic system, then B, C, A are all three are perpendicular. So A star, so in the cubic system, it's clearly evident that A star, B star, and C star will form an orthogonal triad. They will be perpendicular to one another in the cubic system. So the cubic, for cubic, the reciprocal lattice will also be cubic. And for cubic, A star will be, of course, 2 pi over A, because B cross C is A. B star is 2 pi over B. C star is 2 pi over A, C, etc. Right? So this is the meaning of the reciprocal space. Now, what I would like to mention is any point, say any point here, any point of the reciprocal space originating from the origin will have a certain vector in the reciprocal space. So if this point corresponds to the Miller planes HKL, right? So you can put parentheses here as well if you wish, because these points are actually corresponding to the Miller planes, Miller indices of the planes. So this becomes a reciprocal vector in the reciprocal space and is generally represented by G. Okay. So G will be given as a general vector in the reciprocal space is H A star plus K B star plus L C star. ठीक है? तो जब हम इलेक्ट्रॉन डाइफ्रैक्शन और बैंड्स पढ़ेंगे, how bands are formed, the rest of the course, our course will derive heavily from the idea of the reciprocal space. Now the question is, I want to kind of pose to you is the, if I were to write down this statement that the reciprocal lattice is the Fourier transform of the direct lattice. This is true. Now we need to show why this is true. Right. So we'll finish this off in the next lecture, but let me give you the basic idea. If I have, say, some space function gx, some function in space like a lattice, and for convenience I talk about 1D at the moment. So its Fourier transform is given by g e minus I, say some a x, right? And I integrate plus I kx, I integrate over x. This is the Fourier transform of g, small g. Let's call that, represent that Fourier transform of capital G. The variables are now instead of x, they are inverse of x, which is k. Now, if I have a 1D lattice which comprises a train of Dirac delta functions, which is a simple one-dimensional lattice. It's just points that are separated by some periodicity k, which is the unit cell length. Then what is this gx? This gx is a train of Dirac delta functions, x minus ma, right? If I take the Fourier transform of this, what do I get? Correct? That's what I get if I use the sampling theorem. Now, this exactly is the reciprocal space. The reciprocal space. Now I need to prove that. So the Fourier transform of the direct space is the reciprocal space, which looks like this. What I would like to ask you, if this were my reciprocal direct space, what will my, from the construction that I've done, from that construction, what will my reciprocal space look like? Purely from the geometric construction and from the definition of how I'm constructing the reciprocal lattice. What will the reciprocal space look like corresponding to this train of pulses? इसकी रेसिप्रोकल स्पेस क्या होगी इस लैटिस की? ये लैटिस क्या है? ये पॉइंट्स हैं बस एक लाइन में लगे हैं. क्या होगी? शक्ल क्या होगी इसकी? ये फंक्शन की शक्ल क्या होगी? Discrete points से होंगे. So it will still be discrete points. Infinitely disposed. By the way, in all our discussion, we are assuming that there are no surfaces involved. The bulk of the solid is hugely, humongously bigger than the surface. There is no surface physics that we need to know. So the reciprocal space corresponding to this will also be a bunch of Dirac delta functions. The only difference is that this spacing instead of A is now 2 pi over A. Right? This is by construction. Now I need to, so if I were to write down this function is, it's in the K space, A minus N 2 pi a n. And there could be some constant with it, we don't know where. There could be some constant depending on how the Fourier transform itself is defined. It doesn't matter. So this is by construction the reciprocal space corresponding to this direct lattice. Now I want to show that this Fourier transform equals this. If I am able to show that, I will immediately figure out that the reciprocal lattice is the Fourier transform of the direct lattice. Now, mathematically, you've taken many courses in mathematical physics, you are fond of theoretical physics. Can I show that this equals this? Is there an easy way to do that?
Same value can be complete.
ये एक्सपोनेंट्स हैं, ये एक्सपोनेंट्स की ट्रेन है और ये ड्राइव का फंक्शन की ट्रेन है, एक शो ऑफ फंक्शन है। ऊंची बोलो। A equals so what you need to do, you need to write, this is a periodic function. You need to write this as a Fourier series. Write this as a Fourier series. First do this as a homework before you come to class and I'll see if you are able to do that. Write this as a Fourier series. Find the Fourier coefficients. So decompose this as a Fourier series and then compare with this. They will be comparable. So this equals this, which will show that the reciprocal space is indeed the Fourier transform of the direct lattice, the reciprocal lattice. Now, the reciprocal lattice is an extremely useful concept. It helps describe diffraction, as we will see in the later class. The pattern of X-ray that is coming out is exactly the reciprocal. It's in the reciprocal direction. Now, two more things that are very interesting. If in the space group tables, does anyone have space group tables? Any leaf from space group tables? If you look at any entry in the space group table, right? So let's move to M3 bar n. The rightmost column, the heading is reflection conditions. HKL, so if you look at the bottom of FM3N, it's written HKL H equals to N. So this means that only certain reflections will be possible for this space. That is when H equals to N, when H is an even number. Only those reflections will be possible. So only certain directions will be possible that along which X-rays will fall. So in the next lecture, we'll start off by looking at your solution to this problem. And just to give you some motivation, if you have the body-centered cubic Bradel lattice, you find this Fourier transform, you will get a face-centered cubic lattice in the reciprocal space. If you have a face-centered cubic lattice in the direct space, you find Fourier transform, you get a body-centered cubic lattice. So all of these are really important considerations for diffraction studies. Okay? So in the next lecture, we'll deal with diffraction. And we'll also arrange probably a trip to the X-ray machine. Okay?
So, what we got to